Human ingenuity is pretty amazing, isn't it? We've engineered a world of just unparalleled convenience. But, that very same brilliance has also engineered a massive, permanent environmental paradox. So today, in this explainer, we're going to decode the fascinating and honestly quite complex journey of man-made materials. Here's our quick roadmap for today. We're going to define exactly what man-made materials are, dive into the science of plastic as a multi-purpose material, break down the main types of plastics, explore how they impact the environment and our health, and finally, we'll look at potential solutions and our own personal responsibilities. All right, let's kick things off with part one. What exactly are man-made materials? Seriously, take a second right now and just glance around your immediate environment. The screen you're looking at, the chair you're sitting on, your desk, almost nothing you interact with on a daily basis actually exists in nature in its current form. We have quite literally surrounded ourselves with a completely manufactured reality. It helps to think of our material world as a bit of a dichotomy. On one hand, you have natural materials, things like wood, rocks, minerals, and water that we draw straight from the earth. But on the other hand, we rely heavily on entirely new engineered substances, things like glass, plastic, synthetic fibers, and thermocol. These represent a total departure from raw nature. So by definition, man-made materials are born when human laboratories take those natural raw materials and fundamentally alter their molecular structure. We aren't just shaping what nature gives us anymore, we are actively engineering entirely new properties in factories to serve our modern demands. Moving right along to part two, plastic, the ultimate multi-purpose material. You really can't talk about the modern world without talking about plastic. It's essentially an organic polymer defined by one revolutionary trait, and that is its plasticity. This infinite moldability, the ability to take on absolutely any shape and hold it, is the exact reason it has become so incredibly indispensable to nearly every industry on Earth. But if you zoom way, way in, beneath the surface, plastics are actually built on different, hidden structural patterns. Some of them rely on a linear, chain-like arrangement, while others have a circular, ring-like configuration. And it's this microscopic architecture that actually dictates their physical properties and gives us such immense variety in how we use them. That brings us to part three, the main types of plastic. Now, how do we categorize all these variations? Well, it largely comes down to how they react to one critical variable, heat. We have thermoplastics, which can be repeatedly melted down and remolded into whatever you want. And then we have thermosetting plastics, which are locked into place forever once they take their initial shape. This one single distinction dictates basically everything about a product's life cycle. Let's look at thermoplastics first. Because they can be easily melted and reformed, these make up all the flexible, everyday items we constantly use. Think of things like PVC piping, polythene bags, or your standard food containers. This specific chemical structure gives us that lightweight, versatile durability we absolutely rely on. On the flip side, thermosetting plastics offer something just as important, crucial heat resistance. Think about an electrical switch in your house. If that melted under high temperatures, it would be a total catastrophe, right? So for these kinds of applications, the permanence of the plastic isn't just convenient. It's a vital, built-in safety feature. And human engineering has allowed us to highly specialize these thermosetting plastics. Just look at the variety here. We use Bakelite for durable electronics and cooker handles. We use melamine for things like airplane engine insulation. Polyurethane is the go-to for vehicle seating and surfboards, while polyesters are huge in the textile and fiberglass industries. It's basically one foundational chemistry adapted brilliantly to solve incredibly complex engineering challenges across countless sectors. But of course, there is a catch. Let's get into part four, environment and human health. This is the great paradox of plastic. Its absolute greatest strength, that extreme rugged durability, is also its fatal flaw. Because these materials are fundamentally non-degradable, they just accumulate. They don't go away. This creates severe, permanent environmental hazards. What was engineered purely for our temporary, day-to-day convenience now poses significant long-term risks to delicate ecosystems and ultimately to human health. Which leads us to our final section, part 5, solutions and our responsibility. We've successfully engineered materials that will easily outlast us by millennia. The big question now is, how do we actually mitigate the crisis that our own ingenuity created? The true test of our innovation isn't just in what we can build, but in how we sustainably manage it once it's built. So as we move forward in a world drowning in its own inventions, What specific steps are you going to take to balance the scales?